water is flowing through a piping system. Pipe 1 branches out into pipes 2 and 3, where pipe 2 is at the same elevation as pipe 1, and pipe 3 is higher than pipes 1 and 2, by a distance h3. The velocity v1 is equal to 10 meters per second, and v2 is equal to 6 meters per second. The gauge pressure at the beginning of pipe 1 is equal to 300 kilopascals, and all pipes have the same diameter. If pipes 2 and 3 discharge to atmospheric pressure, then what is the height of pipe 3? To solve this problem, we will first write down all the information that we are given. Then we will use the continuity equation to calculate the velocity, v3. And finally we will use the energy equation to calculate h3. Let's write down all the inputs that we have been given. We are told that the heights of pipes 1 and 2 are the same. We've set the reference level equal to the level of pipes 1 and 2. And thus the height of pipes 1 and 2 is equal to 0, with respect to the reference level. Since we're told that pipes 2 and 3 discharge to the atmosphere, the gauge pressure at the exits of pipes 2 and 3 is equal to 0. We are also given that the velocity in pipe 1 is equal to 10 meters per second, the velocity in pipe 2 is equal to 6 meters per second, the gauge pressure in pipe 1 is equal to 300 kilopascals, the density of the fluid is equal to that of water, or 1000 kilograms per meter cubed, and the diameters of all three pipes are the same. In this slide, we will use the continuity equation to calculate the fluid velocity in pipe 3. Let's start by setting up a control volume that encompasses all three pipes. At steady state, the summation of all mass flowing into the control volume is equal to the summation of all mass flowing out of the control volume. Hence the mass flow rate in pipe 1 is equal to the mass flow rate in pipe 2 plus the mass flow rate in pipe 3. Since the diameters of all three pipes are the same, it follows that the cross-sectional areas of all three pipes are equal, and so we can replace A1, A2, and A3 in equation 1 by 8, and we get equation 3. Furthermore, since the density of the fluid is constant, we can cancel out the density and the cross-sectional area from both sides of equation 3, and we end up with V1 is equal to V2 plus V3. Therefore V3 is equal to V1 minus V2, which is 10 minus 6, which is 4 meters per second. Let's apply the energy equation for a control volume with multiple inlets and outlets, and substitute the terms for pipes 1, 2, and 3 into the energy equation. Next we replace the mass flow rate, m dot, for each pipe, by the density, times the cross-section area, times the velocity. Since the product ρ times A is the same for all three pipes, we can eliminate it from the equation, and end up with the shown expression. Then we can rearrange the terms to get an expression for H3. Next, by substituting the values of all the variables, we get that H3 is equal to 92.76 meters above the reference level of pipes 1 and 2. Consider the shown pipe that has a constriction in its middle. As we have seen in the section on the Venturi flow meter, based on the continuity equation, the velocity at the constriction is higher than the velocity at the wider section of the pipe. Furthermore, according to Bernoulli's equation, the pressure at the constriction is lower than the pressure at the wider section of the pipe. Now notice the appearance of the streamlines as they travel through the pipe. At the constriction, the streamlines come closer together, resulting in the higher streamline density. On the other hand, before and after the constriction, the streamlines are further apart, resulting in the lower streamline density. We conclude that when the streamline density increases, the velocity increases, while the pressure decreases. In other words, when the streamline tubes that are bounded by streamlines on all sides become narrower, the velocity within these tubes increases, while the pressure decreases. The lift force acts on an object that has a relative velocity with respect to a fluid in which the object is present. The lift force acts perpendicularly to the relative velocity direction. Notice that we use the term relative velocity to signify that it does not matter whether the object is moving and the fluid is stationary, or whether the fluid is moving and the object is stationary. If the relative velocity is the same in both the aforementioned cases, then the lift force will be the same. The lift force is caused by the pressure distribution around the object. If the pressure is higher on one side of the object than on another side of the object, along the line that is perpendicular to the flow direction, the net lift force is generated. There are three main ways to generate this pressure distribution in an object that has a relative velocity with respect to the fluid that it is in. This can be due to the orientation of the object with respect to the flow, or its shape, or its rotation within its flow. It should be noted that although the term lift can lead one to think that the lift force always acts upwards, this is not true. In fact, the lift force can act in any direction within a plane that is perpendicular to the flow velocity. The drag force, on the other hand, is also a flow-induced force, but it always acts in a direction that is parallel to the flow's velocity. The symmetric object, that has a relative velocity with respect to the fluid in which it is in, and which is oriented so that its symmetry plane is not parallel to the velocity direction, will experience a lift force that acts perpendicularly to the velocity direction. The lift force is due to the fact that some of the flow needs to change its speed and direction in order to flow around the body. Depending on the orientation of the body with respect to the flow, this can cause the streamlines to come closer together on one side of the body, and to be farther apart on the other side of the body. Hence, as we can see in the figure, for the depicted orientation of the shown airfoil, the upper streamline tube is narrower than the lower streamline tube. Hence the pressure above the airfoil is smaller than the pressure below the airfoil. This tends to generate a net lift force that is pointing upwards. Notice how the direction of air velocity after it flows over this airfoil is pointing downwards. This indicates that the airfoil has exerted a net downward force on the air that has caused the air to deflect down. The reaction force from the air on the airfoil points in the opposite direction, or upwards. If this airfoil is the wing of an airplane, this upward force is the lift force that supports the plane in the air against gravity. In this flow simulation, we can see how the streamlines above the airfoil come closer together, resulting in the higher fluid velocity above the airfoil. Notice how the black dots that travel above the airfoil move quicker than the black dots that travel below the airfoil. See how the top dots reach the back end of the airfoil before the bottom dots. The higher fluid velocity above the airfoil causes a lower pressure in that region of the flow. It should be noted that the magnitude and direction of the lift force depends on the orientation of the airfoil with respect to the float. For example, the airfoil in our animation has a lift force that is positive, but if the airfoil is perfectly parallel to the flow, the lift force is zero. And if the airfoil is tilted in the opposite direction, or downwards, the lift force will act downwards. A non-symmetric body that is placed parallel to the flow, such as the shown airplane wing, can't generate a lift force due to its shape. Notice that the lower part of the wing is flat, while the upper part is cambered upwards. As the air flows over the wing, the obstruction due to the curved upper surface causes the streamlines above the wing to move closer together. This causes the velocity of the air above the wing to increase, and its pressure to consequently decrease based on Bernoulli's equation. The net lift force that is generated is due to the difference in pressure that is acting on the upper and lower surfaces of the wing. It should be noted that changing the orientation of the wing with respect to the float can also be used to increase or decrease the lift, as we have seen in the previous section. In some applications where a downward force is required rather than an upward force, an inverted wing is used that generates a lift force in the downward direction. This is used in some cars to push the back of the car down, to increase tire grip on the road under high-speed conditions. In a phenomenon known as the Magnus Effect, a lift force is generated when an axisymmetric object, such as a cylinder or a sphere, spins while its rotational axis, shown here as pointing into the screen, is not parallel to the relative velocity vector of the object with respect to the fluid in which it is present. The lift force acts perpendicularly to the rotational axis of the body, in a direction pointing away from the side of the object, where the rotational speed vector and fluid velocity vector are in the same direction. The lift force is due to the fact that the fluid layer that is in contact with the object adheres to the surface of the object, and moves with the same velocity as the object's surface. This causes the fluid velocity to be higher on the side of the object, where the rotational speed vector is in the same direction as the relative object fluid velocity, and to be lower on the side of the object, where the rotational speed vector is in the opposite direction of the relative object fluid velocity. Based on Bernoulli's equation, the side of the object that experiences a higher relative velocity between the object and the fluid will be at a lower pressure, while the side of the object that experiences a lower relative velocity between the object and the fluid will be at a higher pressure. This pressure difference is what causes the net lift force, which acts on the object perpendicularly to the flow direction. As mentioned before, the Magnus effect can be used to generate a lift force on a spinning object. The lift force acts perpendicularly to the axis of rotation of the object. The direction in which the Magnus force acts depends on the orientation of the flow velocity and the orientation of the axis of rotation of the object. The following are two examples of the application of the Magnus effect, involving vertical and horizontal lift forces. In golf, spin around the horizontal axis of the ball at a rate of up to 9,000 rpm can be used to generate an upward lift force that can allow the ball to travel a longer distance, as opposed to a non-spinning ball. In baseball, the ball can be made to veer left or right, based on its spin direction around its vertical axis. This throw is usually called a curve ball,